Okay, and I think things are being recorded. All right, great. So we're very happy to have our first speaker of OARS in fall 2023. It's Kevin Ren, who's a graduate student at Princeton, and he'll be talking about sharp Furstenberg sets estimates in the plane.
Yeah, thanks, Zane, for the introduction. And yeah, thanks to all of you for coming. I feel very honored to be here. So today I'll be talking about sharp Furstenberg sets estimate, which is a project I worked on joint with Yu-Cho Fu and Hong Wang, but separately. It will be clear in the talk. Okay, so let me introduce what is a Furstenberg set. So in this talk, we will always be working in the plane, and we will say a set E is an S Furstenberg set if there exists a line in every direction that intersects E in a set with Hofstadter dimension S. So in this talk, whenever I say dimension, it will always be Hofstadter dimension. And I guess maybe you need some assumptions like compact and analytic. I will not mention these assumptions, but I guess for technical reasons, you might need some of them. The main question that I want to answer in this talk is, given a real number S between 0 and 1, what is the minimum possible Hofstadter dimension of an S Furstenberg set? So I'd like to point out that the restriction S between 0 and 1 is natural because a line has Hofstadter dimension at most 1. And as an example, a planar Kakeya set is a special case of a 1 Furstenberg set because you have a line in every direction that intersects E in a line segment, and a line segment has a Hofstadter dimension 1. And as you probably know, all planar Kakeya sets have full Hofstadter dimension 2, which is the dimension of the plane. And we will see in the next slide that the same proof will work for 1 Furstenberg sets. So the following was originally due to Cordoba, which is that Kakeya sets have full Hofstadter dimension. And the proof is simply to prove a discretized version, which is that you fix the scale delta, and suppose you have a collection of delta by 1 tubes, 1 for every direction. You show that the union of all of these tubes has Lebesgue measure close to 1, or rather n to the minus epsilon for any small epsilon you pick. And the proof of this follows a standard L2 argument. So you let f be the sum of the characteristic functions of all the tubes. And then you compute the L2 norm, the integral of f squared over the set E. And then because using the geometric properties of the tubes, we know that if you have 2 tubes that are transverse, their intersection is small. And therefore, you could explicitly bound the L2 norm from above, and you get this log n at the end. And then on the other hand, you could relate the L2 to the L1 norm by Cauchy-Schwarz, and therefore you get the measure of the set E is at least n to the minus epsilon, because log is dominated by n to the epsilon. And since epsilon was arbitrary, I believe this proves that Kakeya sets have Hofstadter dimension 2. Are there any questions? And I think it's easy to show that the same proof will work if you replace a Kakeya set with a 1 Furstenberg set. Instead of containing a unit line segment in every direction, like instead of containing the full tube, you instead contain like a large fraction of the tube, like the same quantitative estimate will work. So from now on, I will call this argument the L2 argument. Okay, so now given that previous slide, now we will return to the question. So what is the minimum possible Hofstadter dimension of an S Furstenberg set? And the previous slide answered the question for S equals 1. But for general S, the question is much harder. So the conjecture was originally due to Furstenberg and published by Tom Wolf. And he constructed an S Furstenberg set with this dimension 3s plus 1 over 2 using a lattice grid. And I guess the motivation for this conjecture is basically you have a discrete problem. So this problem makes sense in the discrete case, and the well-known Semmerty-Trotter theorem incidence geometry would give you a tight bound. And the sharp example for Semmerty-Trotter is one of them is a lattice grid. So if you use a lattice grid example and convert it to as Furstenberg said, you would get the same Hofstadter dimension. So this is an example, and on the other hand, you have lower bounds that I show here. You have dimension of E is at least 2s and s plus 1/2. So the first lower bound uses an L2 argument that is very similar. If you kind of do the same argument on the previous slide and tweak it a little, then you would get 2s here. And I guess the second lower bound is slightly different, but it also uses a well-known argument, with the 2n's argument. So I restate the argument here to remind you. So let K be the set of triples. So you have 2 points and a line through the points. So this will be called a triple, and let K be the set of such triples. And I guess we also assume a technical condition that the points are separated. And then you derive the two following bounds. On the one hand, if you fix 2 points of E that are distant at least 1 over 100, then there is only one line through them. And this even works if you replace by scale delta. So technically speaking, to prove such a statement, you'll need to work at a small scale delta, but this conclusion will work at any small scale. And on the other hand, you have the dimension of K is at least 2s plus 1, just by a counting argument. You could pick a line. So because it's a Furstenberg set, it has one line in every direction. So there's a one-dimensional set of lines. And for each line, you pick a pair of points, and each point has an s-dimensional choice. So that's why you get a 2s plus 1 here. And if you combine the two bounds, then you easily get dimension of E is at least s plus 1/2. So just to recap this slide, Wolf, I think in the early 90s, he showed like this upper bound, and he showed these two lower bounds, but there is unfortunately some distance between them. So Wolf conjectured this first bound is true, and the game is to improve the lower bounds to match this upper bound. So in this talk, it will also be helpful to talk about a generalized Furstenberg set. So a set E is a S, T Furstenberg set if there exists a T-dimensional set of lines. So I guess a line is parameterized by a slope and an intercept. So there are two parameters, and therefore the set of affine lines is isomorphic to R2. And therefore it makes sense to view, you could talk about Hofstadter dimension of a set of lines using this identification. So a set E is a ST Furstenberg set if you have a T-dimensional set of lines, so that each line cuts E in a set with Hofstadter dimension S. So how is this related to the previous definition? Well, an S Furstenberg set is a S, 1 Furstenberg set, because if you have a set of lines, one for every direction, so it's basically controlled by one parameter, and hence this is a one-dimensional set in the space of affine lines. And now you could ask the very same question. If you have two parameters S and T, what is the minimum Hofstadter dimension of a S, T Furstenberg set? Are there any questions so far? So basically, this is a basic question we will try to answer during the talk. And during the rest of the talk, I will roughly follow this plan. First, I will give some sharp constructions similar to Wolf's construction for S Furstenberg sets. Then I will give you some easy bounds, kind of similar to those on the previous slide. And then in order to close the gap between the bounds and the constructions, we will introduce two methods. One will involve tools from additive combinatorics and geometric measure theory. Another will include tools from Fourier analysis. And then the last section will be piecing it all together. And before I begin the talk, I'll just give a warning that all of the technical statements are simplified and they might not correspond to those in the paper. But this is all done only because I don't want to talk about too much technical details in the talk. If you have any precise questions, you can ask me afterwards. So let's start with the construction. So there are three regimes, it turns out, for the constructions we believe were correct. So there's S greater than T, T between S and 2 minus S, and T greater than 2 minus S. So the first case, S greater than T, you could let E be the product of an S dimensional and a T dimensional Cantor set. And this has dimension S plus T. And then the horizontal slice. So there exists a set of T dimensional lines, which are the horizontal slices that cut the set in S dimensions. So basically you could get S plus T by this argument. For T between S and 2 minus S, you could use the similarity trotter, like a lattice grid example, and do the exact same thing, and you'll get 3S plus T over 2. Finally, for T greater than 2 minus S, there is a different construction that works. So basically, it's kind of like the first construction, except you pick S-dimensional and a one-dimensional set. So the interval is 0, 1. So it's a S plus one dimensional set. And then, in fact, like you could see this directly, or you could invoke the Marstrand-Mattila slicing theorem to show that you have Lebesgue, on a Lebesgue positive set of slices, like they will intersect E in dimension S. So in particular, if T is, because in particular, Lebesgue measure positive implies Hoffer dimension 2. So this will work for any T between 2 minus S and 2. And so in summary, we have the following conjecture, that the Hoffer dimension of any S T Furstenberg set is at least the minimum of these three bounds. And as you can see, like the first two bounds are equal precisely at the boundary S equals T, and the second two bounds are equal precisely at the boundary T equals 2 minus S. So at least for now, the constructions seem to be airtight, be mutually consistent. Are there any questions about any of the constructions here? Okay. So now that we did the construction, we will move on to some easy bounds. So it turns out that the bounds for the S Furstenberg sets that we've seen before easily carry over and give the maximum of S plus min of S comma T and S plus T over 2. So the first bound was originally due to Lutz and Stahl, who used a computational complexity argument. But it turns out you could also just modify the L2 argument. And Hera, Shmerkin, Yavakoli did this. And for the second bound, you could still use the 2n's argument that I showed you earlier, except T is replaced, 1 is replaced by T. So these bounds, basically follow from techniques that I presented earlier. And I would just like to point out, if S is at least T, then this S plus T matches this one of the S plus T here, and therefore it is sharp. But of course, there is some so now we will begin the section of trying to prove some harder bounds. And the first such bound we will see is through additive combinatorics. So for simplicity in this section, we will return to S Furstenberg sets, which are basically you have a line in every direction, and every line intersects your set E in an S-dimensional set. So recall the bounds we had for them. We had dimension of E is at least max of 2S and S plus 1/2. And there is a special case. If you equate these two bounds, you get S equals 1/2. And these bounds coincide and give dimension of E is at least 1. However, the conjecture, if you plug in 3S plus 1/2, like the conjecture is a dimension of E is at least 5/4. So one natural question is, maybe we cannot get 5/4 right now, but can we get some improvement over 1? And that is what Katz-Tao did in 2000, I think it's either 2001 or 2003. They showed that you could improve this 1 to like some 1 plus epsilon, if and only if you could prove a discretized sum product theorem, which I won't state, but it roughly says that there are no 1/2 dimensional subrings of R. And Bourgain in 2003 proved this discretized sum product theorem. And by combining Katz-Tao and Bourgain, you thus have the following non-trivial improvement over the easy bounds. And I would like to point out that the proof, it's too long to state here, but it's a delicate combination of additive combinatorics and multi-scale arguments. So specifically, if the doubling of a set is small, if a set has small doubling, like that A plus A is comparable to A, then you could impose some structure, kind of like a Freeman theorem type argument. And then you add in some multiplicative structure, and yeah, you do this at each scale, and it's pretty involved, but this is what they did. So this was the first major breakthrough on this Furstenberg problem. And then from there, it took, I think, almost 20 years, but eventually Orpin and Schmerken were able to generalize this not only to S comma T Furstenberg sets, but let me point out that this was proven for the special case 1/2 and 1. So when S equals 1/2 and T equals 1. And I would like to point out that Hera, Schmerken, and Yavakoli were able to prove this theorem for S comma 2S. And the major breakthrough of Orpin and Schmerken is that they could prove it for T just greater than S. And the reason why the S less than T requirement is there is that if S is greater than or equal to T, then as we've seen before, the S plus T bound is sharp. And on the other hand, as soon as T is slightly greater than S, then the conjecture, remember the conjecture was 3S plus T over 2, and this is greater than 2S. So intuitively, we would want some improvement as soon as T is greater than S. And this is in fact what this theorem does. So this absolute constant C will not prove the full Furstenberg conjecture, but it is a step in the right direction. And then an important consequence is which some of you probably have heard, is that using this theorem, Orpin, Schmerken, and Wang were able to prove a radial projection result, which is that I guess I'm missing some hypotheses in this theorem, but basically, if you have X and Y be S-dimensional sets in R2, which are not contained in a line, then the radial projection, then there exists a point in X such that the radial projection from Y is greater than or equal to S. So basically, if you stand at a point in X and look at the set Y, then you will see the full dimension S. And then finally, using this previous radial projection theorem, Orpin and Schmerken were able to use basically solve the Furstenberg set problem for AD regular sets. So the AD stands for Alfors-David regular, and it's basically kind of think of it as a mild generalization of self-summer sets that look the same no matter which scale you zoom into. And it turns out if you have this nice property that you look the same when you zoom in at any scale, then you could do an easier multi-scale analysis. And well, it's still a very long argument, but eventually you could reduce it to the previous radial projection theorem. So I summarize the consequence here, which is that for each s comma t, like the st Furstenberg set, whose line set is T80 regular. So previously we only know that the line set is T dimensional, but now we know if we additionally assume it's 80 regular, then we basically get the desired numerology here. Are there any questions so far? Okay, so I guess there is one last bound that I talked about the s plus t bound. I talked about this bound, but I didn't talk about the s plus 1 bound. So I will talk about it now. So previously, additive combinatorics and geometric measure theory led to the resolution of the 80 regular case. Well, you had to do very intricate multi-scale analysis at each end, additive combinatorics. So that was good for that case. And then on the other hand, we could use a Fourier analysis argument to prove the following another bounds for s comma t Furstenberg sets. And I would like to point out that if s plus t is at least 2, then the minimum will be achieved at this s plus 1. And as we've seen before, this is sharp. So basically, I would like to point out that this theorem predated the previous theorem, and also this previous theorem, it does get s plus 1, but only for T80 regular. So this theorem basically doesn't have the assumption, but only in this regime. And in the next few slides, we will sketch the proof. And this proof will use the high-low method, which I think is a very useful method for dealing with high-dimensional sets in geometric measure theory. So notice that this theorem is very effective when s plus t is greater than 2. So basically, the sets are large. So in the next few slides, I will give a conceptual proof throwing all the technical details under the rug. The actual paper is going to be a little longer because I have to do some dyadic pigeonholing and stuff to make everything work out, but I will hide all these details. So first, I will define a set to be beta dimensional at a scale delta. So I guess, first of all, we're going to always work at a scale delta. And it turns out if you could prove a result at every scale delta, then you prove a Hofstadter dimension estimate. So we'll call a set of delta balls beta dimensional if the set satisfies this Frostman type condition here, which is that if you take any ball of diameter W in the plane, then the number of balls in your set that lie in this W ball decays like cardinality of P times W to the beta. So in other words, of only a fraction W to the beta of the set lies in a given W ball. And then you can make a similar definition for tubes. So in order to prove the previous results, it suffices to prove this following version, which was first proved in my joint work with Yuchio Fu, and then Hongwang and I also proved a slight variant. But basically, it says, suppose you have a Furstenberg set. So the first sentence is basically stating the Furstenberg set assumption that if you have T be a T-dimensional set of tubes, and for each tube, you have an S-dimensional set of balls. So basically, the union P will be a Furstenberg set, a S comma T Furstenberg set. And we also assume S plus T is at least 2. And then suppose we also assume, like after dyadic pigeonholing, let's just assume that we can make every ball lie in the same number of delta tubes of T. If we could do this, then we have this nice bound. R is at most delta times T. So what this means is that a typical ball in a Furstenberg set can only lie in a proportion delta of the tubes in your set. And this will easily, and then if you do some rearrangement, if you double count the number of incidences, then you could easily recover this S+1. That if the richness has an upper bound, then the number of balls in P has a lower bound. Okay. So the proof will involve the high-low method, which I will discuss here. So the key proposition that I use is from Gutzon and Wong's paper in 2019, which is about incidence estimates of well-spaced tubes. And in their work, they needed this key proposition, which is basically, suppose you have a small scale S, which is an intermediate scale between 1 and delta. And then we'll let P to the S denote the S delta neighborhood of P. And then finally, we define a set P to the S like this. Then we will have this following incidence estimate that the number of incidences between P and T. I guess I didn't define incidences. It's basically the number of pairs the number of pairs of balls and tubes such that the ball intersects the tube. So this is what this I P comma T means. And it turns out you could upper bound it by two things. So the high frequency part is, so it turns out, so the way to prove this is that you basically write this. So you write the number of incidences as an integral. And then you write it as an integral of f times g, where f is the characteristic function of the balls in P, and g is the sum of the characteristic functions of the tubes in T. So kind of like what we did before. And then you use, I guess, Plancherel's identity, which is that integral of f times g is equal to the integral of f hat times g hat. So you do a Fourier transform. And it turns out if you move from physical space to frequency space, and then divide into a high frequency portion and low frequency portion, then the high frequency portion is given by this red term, and if the low frequency term is given by this blue portion. So, and this blue portion could be interpreted as kind of like convolving P and T with like a mollifier at with a mollifier at scale S. It basically smooths out like a delta ball to an S delta ball, kind of like what you see in this figure. So I guess you could imagine that this proposition, such a proposition could be true, and I hope I explained where the high and low parts come in. I could explain more at the end of the talk. But just to summarize the takeaway, you could bound the number of incidences by either this main term or something at a different scale. Like basically this low frequency term will allow you to change your scale delta to S delta. And this is very good for induction. So with this proposition, we will move on to the proof. So as I said, is based on induction, and let S be this intermediate scale S to minus epsilon. And then I just rewrote the equation on the previous slide. So we have two terms. And let's suppose the first bound holds. Then we will, so now we will use the fact that the number of incidences can be lower bounded in two natural ways. The first way is given a tube, every tube, I guess let's make the assumption that every tube contains the same number of balls. So in this theorem, let's just assume each PT has the same cardinality. And then, so we basically get this, we get for each tube, we have P sub T many balls on that tube, and therefore the incidences is at least T times PT. And then we also know that because each ball in P is R rich, so each ball in P lies in R many tubes of T. So we also get this bound. So we have 3 bounds for I. We have this bound, we have this bound, and this bound. So we will take these last 2 bounds, we will raise them to the 1/2 power. So basically I of PT is at least the square root of this times the square root of this, and then you compare against this bound here. And then after you do some algebra, you eventually get R is at most this. Where I dropped I basically absorbed the S to the 1/2 in this less than approximate term. And then finally, you could relate this to delta times T. And this last implication is where the S plus T greater than or equal to 2 is ultimately used. Now, if the second bound holds, then as I said, you will basically just do the same argument at scale S delta. And there is a slight annoyance is that if you thicken the balls to S delta balls, then you might run into some overlapping elements where you have two balls that are close originally, and if you thicken them, they will be exactly the same. So it turns out you could handle these duplicate elements through some pigeonholing, and we will not care about this. And you will just imply induction. And so in either case, you get the desired bound R is at most delta times T. So I hope this calculation illustrates the use of the high-low method, which is that either the high frequency part dominates and then you get your desired numerology, or you have the low frequency case, and then this allows you to change scales. And you keep changing scales until you arrive in a situation where the high frequency dominates. Or I guess maybe you will go to a large enough scale. So like if the low frequency part always dominates, then eventually your scale will be so small, then a trivial bound will work. Or so large, I mean. So I guess that was the base case. I forgot the base case of this induction, but the base case would take care of if you are always in the low frequency case. So in summary, using the high-low method, we were able to use the high-low method in Fourier analysis to prove this sharp bound S plus 1 when T is greater than or equal to 2 minus S. And then I'll just also summarize the previous 2 slides. If T is at most S, then you have the L2 argument from before, from Harris, Schmerk, and Yavakoli. You get the S plus T. And then also then there is a non-trivial part if T is between S and 2 minus S. Then after you do 100 pages of additive combinatorics, then you could achieve a sharp bound for 80 regular sets. So it seems like, and then recall the conjecture is basically, so basically the conjecture, in order to prove the conjecture, we only need to deal with the middle case. The other 2 cases have been solved. So the million-dollar question is, how do you prove the middle case for general sets? I will briefly pause here. Are there any questions about what I have said before? In particular, I hope the statement of the Furstenberg problem is clear. Like, what is ST Furstenberg sets? Okay, so moving on. So basically these 3 bullet points were basically the state of the art until my paper with Hong Wang. So now we will move on to my contribution with Wang. So I guess, so basically Orpin and Schmerken were able to prove this result for 80 regular sets. And it turns out if you want to prove some result for general sets, then what you could do is you partition the set of scales into blocks so that on each block you look AD regular. And the hope is if you have a good AD regular result, then you could upgrade it to the general case by using the AD regular case on each block. And this is exactly what Orpin and Schmerkin did in both their papers in 2021 and 2023, which is that if you could somehow decompose into blocks and prove a 3s plus tj over 2 result on each block, then you could combine the results on the different blocks and lead to an 3s plus t over 2 result for the entire thing. So by saying this, I swept a lot of important information under the rug. Like I didn't define what does it mean to be a Furstenberg problem at a given scale or between two scales. Like I did not define this, but assuming you could define, but this is basically what Orpin and Schmerkin did. They were able to make sense of what a Furstenberg problem is between two different scales. And then I'll just say that it corresponds very naturally with our intuition. So you could just imagine each block is, without loss of generality, is like the regular Furstenberg problem. It's pretty similar. So it seems like we would be done because given a general set, we could always partition into a set of a finally many scales on which it looks like AD regular. The price to pay is that the TJs might change. So it seems like this multi-scale decomposition would solve the problem. But there is a slight issue that if TJ is less than or equal to S or TJ is at least 2 minus S, then remember the conjecture. Then we will be in one of the first or the third case. We do not get the third bound. And I guess the main idea we had, so Orpin and Schmerkin had a partial result, but we were able to have the following proposition, which is that given a t-dimensional set, we could partition the set of scales into blocks on which it either looks TJ AD regular for TJ in S, 2 minus S, or it looks TJ semi-well spaced. And the semi-well spaced I will define on the next slide. But this proposition is the key, is one of the keys to proving Furstenberg in the general case. So I should mention that Orpin and Schmerkin they basically were able to do half of this proposition. They were able to say, allow TJ to be in S, 2, which is why they were able to get a partial bound. But the main novelty of our proposition is that we can make TJ in S, 2 minus S. And if you're in S, 2 minus S, then you do get the 3s plus TJ over 2 bound. And therefore the remainder of the problem is to prove the 3s plus TJ over 2 result for Furstenberg sets that are semi-well spaced. And then here I define what semi-well spaced is. It's basically what you would imagine if you try to go the opposite direction of AD regular. Instead of looking the same at different scales, you will look like very large at large scales and very small at small scales. And the exact quantification is you look at least 2 minus S dimensional at large scales and at most S dimensionals at small scales. So basically, using this proposition, we are able to reduce the Furstenberg set problem to the semi-well spaced case to show that you could get a 3s plus TJ over 2 result. Okay. And then And then to solve this case, we basically reduce to, so basically the remainder of our paper is solving the semi-well-spaced case, which will also require the high-low method. So the assumptions are here. If you have E being a semi-well-spaced set between scales at delta and 1, and for each tube, you have a S-dimensional set of balls. So the first sentence is still the S comma P Furstenberg set assumption. And then now we will, as before, we will let P sub R be the set of R-rich balls. And then assuming that R is greater than this threshold, we will get the following similarity-Trotter type bound. So the number of R-rich balls is at most T squared over R cubed, where this less than approximate hides epsilon losses. So I'd like to mention, first of all, that the case S equals 0 was proved by Gutzman, Solomon, and Wang, because if S equals 0, then semi-well-spaced is basically well-spaced. So, and in fact, the proof of our theorem will be basically a streamlined version of their argument, where so the first thing is to choose a good scale W between delta and 1. So this delta is, I guess, the scale delta that I defined in the previous slide. So first you choose this good scale W, and then you partition the set of tubes into W times 1 cells. So you basically do a cell decomposition here, which is exactly the same cell decomposition as Gutzman, Wang. And then I guess the point where we diverge is that then I proceed directly. I don't do induction. So I apply an L2 argument to each cell to basically bound incidences in each cell. And then I will use the high-low method to piece together the different boxes. I will make some brief comments on why this is motivated. So if you notice before, so if you look at the semi-well-spaced definition, I told you that T looks high dimensional at high scales and low dimensional at low scales. So if you are at a low scale, in the progress so far slide, I said that an L2 argument gives a sharp bound. So basically, if the dimension of the set is really low, then L2 arguments would be the best. But on the other hand, for high scales, I told you is at least 2 minus s dimensional. So when T is greater than 2 minus s, then we want to use a Fourier analysis argument. We use the high-low method. And this is exactly the philosophy here. So we apply the L2 argument when the tubes look very sparse, look very low dimensional. And then we use a high-low method for the different boxes. So piecing together different boxes is essentially like doing an argument at a higher scale. And that is why our argument is able to exploit the semi-well-spaced nature of T. So, and then I'll just also further comment, if W equals 1, then our argument will give, if W equals 1, then you basically do the L2 argument on the entire square. And you could, and then the L2 argument will give you this bound, a T squared over R squared. So it is really the fact that we choose a good scale W that we could upgrade this R squared to R cubed. And I think this is probably like the most beautiful thing of the proof. So are there any questions so far? So basically, to summarize, there were 2 main ingredients. The first main ingredient was this proposition that decomposes a set into scales that are either AD regular or semi-well-spaced. And then the next proposition is to solve the semi-well-spaced case. And again, I basically skipped over all of the technical details. This is just a high-level explanation of the tools involved. Okay. So let me just restate the conclusion, is that we were able to prove that the Hasse dimension of any S, T Furstenberg set with T semi-well spaced lines set is at least the conjectured bound. And then combining with the previous multi-scale decomposition and Orpin-Schmerken's AD regular result, we were basically able to establish the full conjecture. So in the remaining 10 minutes, I will give some applications. So the first application is orthogonal projections. So there is this well-known problem that if you have an arbitrary board. So let me first recall the so basically, we want to look at arbitrary Borel set in the plane K that is T-dimensional. And then we want to investigate the orthogonal projections onto various directions. So if you recall Marstrand's projection theorem, you know that for most directions, if you project onto most directions, you should preserve the dimension of the set. So if you look in most directions, the orthogonal projection will exactly be T-dimensional. But then the question arises, what can you say about the dimension of the exceptional set? Basically, what can you say about the set of directions in which you are less than T-dimensional? And I guess you could even ask about the set of things that are less than U-dimensional for any U between 0 and minimum of T, 1. So this is known as the exceptional set problem for orthogonal projections. And there was a conjecture that the right-hand side should be this, 2U minus T, 0. And the reason why this conjecture was formed was because the endpoint case were solved. So Bourgain had a nice theorem saying that if U equals T over 2, then if you plug in T equals 2, you get 0 here. So the case U equals T over 2 was solved by Bourgain. This was, in fact, the major breakthrough. This was, in fact, related to the breakthrough that I said earlier on the discretized sum product problem, that if you have a T-dimensional set, then basically everywhere your projections will look at least T over 2 dimensional. So U over T over 2 was solved using an additive combinatorics. And on the other extreme, U equals min T, 1 was known previously due to Kaufman and Falconer. So Kaufman in the case where T is at most 1, and Falconer in the case where T is greater than 1. And I should point out that Kaufman used an LT argument, Falconer used the kind of high-lowish argument too. So, and then Oberlin came along and conjectured that the natural interpolation, the linear interpolation should be the desired bound. So, and then basically we were able to prove it, and it follows easily from the Furstenberg set estimate, which I'll present here. So, by the way, to make this rigorous, you should work at a fixed scale delta and do what I do here. But I'll just present this simplified exposition. So we will suppose that the dimension of the set E is greater than 2U minus T. So let's just unpack this statement. What does it mean for your exceptional set to be large? Or like, what does it mean to be in an exceptional direction? So for each exceptional data, the projection is small, and therefore we could cover K by a T minus U dimensional set of lines, L theta. And then basically the union of these, and then the union of these lines will have, basically you add up the dimensions S and T minus U, you get S plus T minus U. Okay, and then however, L will be a dual S, T Furstenberg set. It is because for each X and K, there is an S dimensional set of lines. corresponding to the exceptional directions. And basically, in the plane, like the dual Furstenberg and the Furstenberg set problems are equivalent, and basically you could use this 3s plus t over 2 bound, and then you get a contradiction. Okay, so basically using the Furstenberg set estimate, you are able to prove exceptional set estimate on orthogonal projections. And then the final application I'll present is the discretized sum product problem. So this is basically related to what I said on one of the very first slides, that in order to make some improvement on Furstenberg, you needed a discretized sum product theorem. So interestingly enough, so now we could come back and use the full Furstenberg conjecture to make some more progress on the exact same discretized sum product problem. So basically supersedes the original result, but I'd like to point out the epsilon result was needed to prove all of this. And I think that's quite cool. But anyway, so suppose you have an S-dimensional set where S is between 0 and 2/3, then either the sum of the sets or the product of the sets will be larger than, so the trivial bound is delta to the minus S because A has cardinality delta to the minus S. And in fact, we could do better. We could get a S/4 improvement. And the proof is by using a framework proposed by Alkes in the discrete setting, but it easily carries over, that you consider the set A plus A times, it should be a dot A. And this will in fact be a S comma 2S Furstenberg set. And the reason is because you could construct a 2S dimensional set of lines. So it's 2S dimensional because it has two parameters, and each and B and comma C are each S dimensional. So this line set is 2S dimensional, and each line contains an S dimensional set of points. And therefore, it's a S comma 2S Furstenberg set, and you use the bounds that I have for that. Okay. So just to summarize, we were able to prove that the Hofstadter dimension of any S comma T Furstenberg set is at least a minimum of S plus T, 3S plus T over 2, and S plus 1. And we were able to show sharp constructions for each bound and also prove them using a variety of methods. So the S plus T bound was proved by an L2 argument. The S plus 1 bound is proved using the high-low method, and the 3S plus T over 2 bound is proved using a combination of a lot of different techniques. And then finally, we discussed some applications to discretize sum product and projection problems. And then I guess for future directions, we could ask the same questions in higher dimensions. And we could formulate the S Furstenberg and the S comma T Furstenberg set problems. And however, unlike in 2 dimensions, the higher dimensions are so the 2 problems are quite different, because the S Furstenberg problem is at least as hard as Kakeya. Like even S equals 1 is unsolved in, say, R3, while the S comma T Furstenberg problem could probably be solved using the known techniques. And this is because, interestingly enough, the condition of having one tube in each direction is much stronger in higher dimensions than being for example, in R3, having one tube in each direction is much stronger than the statement that you are a 2-dimensional set of tubes. And it is because in 2D, there is not really that much of a difference. But in higher dimensions, this makes a world of difference, because in particular, you could have concentration of tubes near hyperplanes, and this will lead to different phenomena. But it will be interesting to see whether the results and methods I talked about here could generalize to higher dimensions. And with that, I would like to close my talk. Thanks for listening.
Right. Let's thank Kevin for giving a nice talk. Use the reactions for. And then let me stop the recording.